Welcome to the board. Now we will discuss regarding opening and closing operations. What is meant by opening and what is meant by closing. So opening means it is we are using opening generally for this smoothing. Okay. So opening generally smooth is the counter of an object. What is meant by counter? Counter is the outline or shape of something. So here counter means the outline or shape of the object uh, of the object. So opening generally smooths the counter of an object means the outline or shape of the object and breaks narrow isthmuses. What is meant by isthmuses? A narrow strip of land with the sea on either side, which is forming a link between two larger areas of land. So, here and here water is there. A narrow link is connecting between these two water areas. Okay, so it breaks in narrow isthmuses means it is breaking this narrow joining, okay, of two objects and eliminates thin protrusions. What is meant by protrusions? Protrusion means it is something that sticks out from something. So these two are joined by the narrow link. So here we are breaking that narrow link and which eliminating protrusion. So this joining we are eliminating. Okay, that we are achieving from the opening. And what is meant by closing? Closing means it tends to smooth sections of contours, so sections of the outline or sections of the shape, but it generates fuses narrow breaks and a long thin gulps. What is meant by fuse? Fuse means it is a join or blend to form a single entity. So within the narrow links, it generates fuses. It means it is joining narrow breaks, whatever the breaks there to do the smoothing of the sections for the outlines or the shapes, contours. So that fuses narrow breaks, it generating that breaks, and long thin gulps eliminates small holes and fills gaps in the contour. So it is smooth. Suppose this is the area, it is joined by this, it is smoothening and eliminating this, and all the gaps here also filling, and small holes are also eliminating. In this way the closing doing the operation. And the mathematical expression and definition for the opening and closing is the opening of set A. So we are applying the opening operation upon the set A, and upon the set A by structuring element B. So here we are using the structuring element B on the set A is denoted with the A circle B. Okay, so opening of set A by structuring element B is denoted with A circle B and is defined by the set expression A symmetric difference and plus circle B. This set expression giving our opening of set A by structuring B, A circle B. And the closing operation mathematical expression is the closing of set A by structuring element B, and it is denoted by A circle B and is defined as A plus circle B symmetric difference with the B. Okay. Now the opening of set A by structuring element B is denoted by A circle B and is defined as union of, you can also define this as not only by this, it is the union of B of Z such that B of Z is subset or equal to A. Okay. Then I'll show some example for the opening and closing. See here. So this is the structuring element B and this is the set A, this one, and this is the structuring element B. So the structuring element B rolling along the inner boundary of A. So rolling along the inner boundary of A. This is the set structuring element. Then this dot is indicating the origin of B. Now the heavy line is the outer boundary of the opening. This one. The heavy line is the outer boundary of the opening operation. This opening operation is drawn with the heavy line. This is the opening boundary, outer boundary, and the complete opening is a shaded, this one. This shaded one is the complete boundary, and we did not shade A with for the clarity. Okay, so this is opening example. Now I'll show you closing example. See here, this is the closing example. So this is the set A and this is the structuring element B rolling on the outer boundary of set A. The heavy line, this heavy line is the outer boundary of the closing, and complete closing is shaded, and we are not shaded A for clarity. Okay, this is the closing expression. Now I'll show you another example. So this is the topic under the morphological operations. So morphological opening. Okay, so here in this picture, in this slide, we can see the morphological opening and closing operations. So this is the set A. This is the set A, and this is the SE structure element B. Okay, then it is sliding over the outside boundaries. Then we applying the asymmetric B operation. Then symmetric difference, asymmetric difference of B operation. Then this is the resultant one, and upon that, if you plus circle B operation if you do, then this is the resultant one. Then final morphological opening operation giving this is structure, and this is the formula for that one. This is the output. In the similar way, we applying the morphological closing operation first upon the set A. So this is the uh, outsider movement, boundary movement for the SE structured element. So if you did if you do the A plus circle B, this is the resultant one. And then if you do the A plus circle B symmetric difference with the B, then this is the output. So this is the output for the morphological opening, and this is the output for the morphological closing. Now we will see duality. So by the observation of opening and closing, these two are dual each other. So the opening and closing are duals of each other with respect to set complementation and a set reflection. Set complementation property, and by the set reflection property, based upon these two properties, the opening and the closing are duals of each other. So A plus A circle B whole complement is equivalent to A complement circle B complement. In a similar way, A circle B whole complement is equal to A complement circle B complement. And now coming to the properties of opening and closing. First, properties of opening. So A circle B is a subset, subimage of A. And if C is a subset of D, then C circle B is a subset of D circle B. So whenever A circle B is a subset, subimage of A, this is one property. So A is a set, and after we doing A circle B operation, opening operation, then it is also a subset, subimage of A. This is the property saying. And second property of opening is, if C is a subset of B, of D, C is a subset of D, then C circle B is also subset of D circle B. Okay, this is another property. Another property is A circle B is equivalent to A circle B. Okay, so here it is acting as an identity element. These three are the opening properties, and the similar way properties for closing. Similarly, A is a subset or subimage of A circle B, and if C is a subset of D, then C circle B is a subset of D circle B, and A circle B is equivalent to A circle B. Same similar properties for opening and closing. These are the properties. Now I'll show some example for the homological structuring element and the opening and closing operations. See, this is the set A noisy image. A noisy image is the set A, and our structuring element is this one. So this structuring element we are applying upon the A set, upon this noisy image. Okay, then if we do the erode operation on A, then this is the output of erode operation. This is the output of erode image. So this is the formula for erode image, you know. And then suppose if you apply the opening operation upon this image, means we are applying this into this, then this is the output of the opening operation. This is the formula for that one. This is the operation we applied upon this. Here B is this one, and suppose we are doing closing operation, then the closing operation is this one. This is the closing operation. Okay, so this is the closing operation. And then if you do the dilation, erode and dilation, so dilation operation, this is the output we are getting from this noisy image. So observe, this is the erode operation output for this one, and this is the opening, and this is the dilation, and this is the closing. So in these ways we are getting different types of outputs from the noise images. Based upon our requirement, we apply the operation dilation, erode, opening, and closing. Now, the other type of transformation, which is very importantly using in the morphological algorithms is the hit or miss transformation. So, what is actually the hit or miss transformation means? This is the transformation which is a general binary morphological operation. So, we are using this operation in the binary morphological operation, and that can be used to look for particular patterns of foreground and background pixels in an image. So within an image, the foreground or background uh, pixel patterns it is looking, which is the hit and miss transformation. It is actually the basic operation of binary morphology, and almost all the binary morphological operators can be derived from it. So, in most of the binary morphological operators, we are using this hit and miss transformation. And with other binary morphological operators, it takes as input a binary image and a structuring element SE, and produces another image as output, another binary image as output. This is the morphologic hit and miss transformation operation which we using in the morphological operations. Now, see, here is an example. For this example, suppose B denotes the set composed of D and its background. The match or set of matches of B in A denoted with the A with the tensor product of B. So what is A tensor product of B means, which is the expression we define this A tensor product of B in the expression A set difference with the D intersection with the A complement symmetric difference uh, of W minus D, whereas the B containing the B1, B2, and B1 is the object and B2 is the background of this B1 object. So our A tensor product of B is equivalent to A symmetric difference of B1 means the object intersection A complement symmetric difference with the B2 means with the background. Now see, this is the B. So here this is C union D union E is in a frame. For this, so this is whole set A, and a window W, the local background of D. For this is the local background with respect to W minus D. So the W minus D is given this one with the origin this dot. Next, the complement of A is giving this one. So the complement of A, for this the complement of A is this one. Complement means the opposite one. So the unshaded one is shaded, the shaded one is unshaded here. In the picture view, we shown the difference in this way. And the complement of A is this one. Now we are applying the erosion operation upon this. So the erosion of A and D is giving this one. So we applied the erosion operation. And after that, we are intersecting intersection of A and D. Okay, the intersection of D and E is giving this one. This is the intersection of D and E, and the location of origin of D as desired, the dots indicating by this one. The dots indicating this one. So the dots indicating the origin of C, D and E by this operation. And so for the morphological operations, we completed the basic preliminary operations, transformations, expressions. Now we are discussing some basic morphological algorithms. The first morphological basic algorithm is the boundary extraction. So within an image, we are extracting the boundary. How? The boundary of set A can be obtained by first eroding. So here we are applying the eroding operation. By first eroding A by B and then performing the set difference between A and its erosion. So this boundary extraction is denoted with the beta of A is equal to the set A and apply the eroding of eroding of A by the B, then the set difference A minus A symmetric difference of B. So this is the expression we are using to extract the boundary in the morphological algorithms. I'll show an example how to extract the boundary. Here see, this is the set A and we are eroding by the B. This is the B. So we are applying the erosion. So this is the structuring element SE and applying erosion operation means A set difference, symmetric difference with the B, A by B. Then this is giving the result by this expression. Now the boundary given by this set is the difference from A to this. The difference from this to this is giving this one. The boundary is extracted. Okay. So in this way we are applying the doing the boundary extraction. I'll show another example of boundary extraction. So this is the simple binary image with respect which is in a representation in white color, and when we apply that formula A minus asymmetric difference of B, then this is by using the structuring element, then the boundary is extracted. Okay, now we will see another basic morphological algorithm. Another second basic morphological algorithm. First one is boundary extraction. And next one is hole filling. Hole filling, basic morphological algorithm. What it is saying, a hole filling means first we have to know what is a hole defined in the morphological algorithm in the image processing. A hole may be defined as a background region surrounded by a connected border of foreground pixels, which is a background region, and it is surrounded by a connected border foreground pixels, that is the hole. Then let A denote a set whose elements are 8 connected boundaries. 8 connected one in this way. In this way 8 connected one, and each boundary enclosing a background region. We know each one is enclosed with the background region, that is a hole. And given a point in each hole, the objective is to fill all the holes with ones. So here we are giving a point in each hole. Suppose this is a hole, we are giving a point, and this is a hole, we are giving a point. And the objective of hole filling is fill all the holes with the ones. Fill all the holes with the ones. This is the goal, objective of the hole filling algorithm. Now see mathematical expression for hole filling. So forming an array x naught of zeros. So x naught array containing all zero elements, the same size as the array containing A. Whatever the set A we are taking, for that set A size, the same size array we are taking representing x naught, which containing all zero values, except location in x naught corresponding to the given point in each hole, which we set to 1. So when we are applying this x on this A, and except the location this x naught array occupied in the A, we all remaining, okay, except the x naught, the zeros occupied in A, except those accepted values we are setting to 1. Okay, so remaining the occupied x naught 0 values are in 0, and except it is not occupied, that is represent set to 1. That is a hole filling algorithm. So for that we are taking x of k, which is defined, expressed as x k minus 1 plus circle B intersection with the A complement. And here the k is from 1 to 3 and so on. And to stop this iteration, looping, continuation, to stop the iteration, when we stop, if x is equal to x of k is equal to x of k minus 1, x of k is equal to, if x of k minus 1, we are stopping the algorithm. Now see the example for that one. See this example. So for this hole filling we are doing for this. So this is the set A, and set A is shaded. A complement is this one. Next, complement of A is this one. Structuring element we are taking is this B. And then initial point inside the boundary we taking this one. And after that, this one also we taken, this one also we taken the points. Next, this one we taken. In the similar way, we are selecting the points in step-by-step manner, and the final result is x8 union A. So when we reached 8, this is the condition of xk is equal to, this is the condition, x of k is equal to x of k minus 1. That's why here we stopped the algorithm. This is the output. This is the output image. And I'll show now by the image how this happened. This is the binary image. So white dot inside one of the region is the starting point for the hole filling algorithm, and resulting of filling that region, see the difference. Okay, so accept the hole filling, this is the accepted one. Okay, then doing step by step, repeating that one until k of x of k is equal to x of k minus 1. After repeating that one, at the final iteration, This is the output we got. All are with the ones, represented with the ones. And now coming to the next algorithm, morphological algorithm, extraction of connected components, morphological basic algorithm. Third one. In this, central to many automated image analysis applications are based upon extraction of connected components. From central to many automated image analysis applications, it is very important one, extraction of connected components of morphological algorithm. In this, suppose let A be a set containing one or more connected components and form an array x naught. You know x naught is containing all 0 elements. The array x naught containing all 0 elements. And the size of the array is same as the size of the set A. And except at each location known to correspond to a point in each connected component in A, which is set to 1. This is this is previously we discussed. So except at the place where x naught is occupied, in that place we are setting that to 1. Now see mathematical expression for the extraction of connected components. So xk is equal to xk minus 1 plus circle with b intersection with the a. So b is the structuring element. So we are plus circling the array x k minus 1. We are plus circling with the b, the structuring element, and then we are doing the intersection with the set a. And how much we are iterating this until k is equal to xk minus 1. When we reach this condition, we are stopping the repetition. Now I'll show you an example for this. See, this is now extracting connected components. So from this connected components, see all these are connected components we are extracting. For this A set, we are taking the structuring element, this one, B. Okay, so this is the array. Now, we are initial array containing a 1 here. Initial array 1. We set this one as 1. So, in the region of connected components, we are repeating this step from here to here, here and here, and we are repeating all these steps, and when we reach the condition to stop the iteration, then finally we are getting the output this one. Okay, so in this way we are applying. I'll show the application on image. See this. This is the x-ray of chicken fillet with a bone fragment. Chicken fillet bone fragment. Okay, then thresholded image of this one is this is the thresholded image, and image eroded with a 5 by 5 structuring element of ones is the image of this one. And then number of pixels in connected components are we are extracted from here are listed here. The connected components are these, and the number of pixels connected components at that position are these. In this way we can extract the values which are connected ones. And next, another basic morphological algorithm is the convex hull algorithm. You know the convex hull algorithm. When we study the DA subject, we know very well the convex hull algorithm. So it is taking a set A is said to be convex if the straight line segment joining any 2 points in A lies entirely within A. Then this is the convex. Then now the convex hull of H or of an arbitrary set S is the smallest convex set containing S. This is the convex hull algorithm. The same definition wherein the subject. Now here in the morphological algorithm we are applying that one as a mathematical expression. For that, let bi, where I is equal to 1 2 3 4, it is representing the 4 structuring elements. Bi is having 4 structuring elements, and the procedure consists of implementing that equation. How we can implement that equation? By the iteration taking by the k. So xi of k is equal to xk minus 1 uh, xk minus 1 tensor multiply with the bi tensor product with the bi union with a. Here x naught of I is equal to a with this condition, and when the procedure converges, then x k of I is equal to xk minus 1 of I, and for that we have to let our di is equal to ki xk of I. So the convex hull of A with these is defined as convex hull of A is equal to C of A is equal to union of I is equal to 1 to 4, because here 4 structuring elements 1 to 4 D of I. This is the expression. Now see the example. So the structuring elements are these. This is B1, 4 structuring elements. This is B2, B3, B4, 4 structuring elements. And the set A is this one. And from this is x naught 1 of A. This is set A. And then this is the result of convergence with the structuring element shown in here. So this is the resultant one from this, and this is the resultant one from this, and this is the resultant one from this, and so on in a step by step. Next, this is, and this is from the result of this, and now this is the convex hull, giving by this expression. Okay, so the final result is this one. With this final result, we can more elaborately see the output. See, by the result of B1, these shaded boxes, and by the result of B2, these dashed cross-lined in this direction, and by the result of this cross-lined in this direction, and parallel lines in this direction for this structuring element. So the result of a limiting growth of the convex hull algorithm to maximum dimensions of the original set of points along the vertical and horizontal directions. And now we will see another morphological basic algorithm, which is thinning. So the outer borders and inner borders. When we want to do the thinning on the image borders, then we apply thinning morphological algorithm. The thinning of set A by a structuring element B is defined as A tensor product of B is equivalent to A minus A tensor product of B, and A intersection with A tensor product of B complement. For this, we can define more useful expression for thinning asymmetrically based on a sequence of structuring elements. So the sequence of structuring elements which are symmetrical, then the sequence of structuring elements are B1, B2 and so on, Bn, the structuring element, where Bi is the rotated version of Bi minus 1. So whenever it is reached I minus 1, then it is rotated. Then the thinning of A by a sequence of structuring elements is given by A tensor product with the set B is A tensor product of B1, tensor product of B2 and so on. Finally, tensor product with the Bn. This is the expression. Now see an example for that. This is the example. See this one. How thinning we can achieve. So the sequence of rotated structuring elements are all these. And for thinning, we are applying all these structuring elements sequence. And this is the set A. Upon this, we are doing thinning. And this is the resultant of thinning for the first element, and this is for the second, this is for the third, this is for the fourth, this is for the fifth, it is for sixth, it is for seventh, it is for this. Okay, and after doing this, the results are convergence. So here we converged with this, and after that no more changes within this, and this is the final converted M connected thinning operation. This is the output we are getting. So total one second. So total 5 morphological algorithms we discussed in this board. So many morphological algorithms are there. So in this board we covered opening and closing, hit or miss transformation, morphological image processing, boundary extraction morphological algorithm, hole filling morphological algorithm, extraction of connected components morphological algorithm, convex hull morphological algorithm, and also the thinning morphological algorithm. Okay, and see all the lectures in Tritva Jyoti KIRAN blogspot.com and in Tritva Jyoti YouTube channel. Okay, see you in the next board.